All right. How are we doing? All right. I got a little off yesterday. I was thinking in my head that the test was only over the fundamentals. So that's what I told you. But it's also going to have the alpha plus beta identity. So clear your desk. I'm just kidding. No, we'll have our test on Monday, our quiz on Monday, but it's going to have those alpha plus beta identities on there. Okay? And we're not going to start talking about them until Monday or show you the proof. I might have a chance to show you the proof today. But basically, I can show you there are some kind of patterns to memorizing that are helpful or that make it a little easy. For instance, when I say alpha plus beta identity, I'm talking about when the angle is the sum of two angles. So for instance, alpha might be 10, beta might be 12. So the sum of the two angles is 22. Problem is, I don't know what alpha is. I don't know what beta is. So in a problem like this, what this formula is going to allow you to do is, even though I might not know anything about the angle that's 22 degrees, if I know stuff about the angle that's 10 and 12, I can rewrite this into a bunch of little trig expressions that use 10 and 12. So we'll talk about how that's useful to us later. But bottom line is, here's your little formula. It is not the distributive property. You don't come in here and go sine of alpha, sine of beta, plus sine of beta and call it a day. I mean, you might, but you're going to get every one of them wrong. And remember, the distributive property, it only works anyway when it's a number right there, right? And you're multiplying a number in. And sine's not a number. What is sine? It's telling you to find the ratio of the two sides of the triangle that has an angle that's that big. Right? So it's not even a number. You don't distribute it in there. It's just an indication of what you're doing with this angle. So don't distribute it. This is the property, and the proof would show you why, although the proof is not going to help you remember it because it's a pretty involved proof. But what you do is you take the sine of this times the cosine of that. So you start with sine of the first angle times cosine of the second angle. And then whatever that is, if that's a plus, you bring the plus over, and then you switch it up and you say cosine of the first angle, sine of the second angle. And you multiply those together. And that's your alpha plus beta. And then the only thing that changes when you go from sine of alpha plus beta to sine of alpha minus beta is this becomes a negative here. But it's still sine of the first, cosine of the second, minus cosine of the first, sine of the second. And getting these in the right order does mean something occasionally. Like right here, because both of these are positive, it wouldn't have mattered if that was first. But on this one, where this is positive, that's negative, if you had this part first, and then you had minus, and you had this part second, you'd miss it. And by the way, I give no partial credit on these quizzes. So you get one thing wrong, you've missed that all of it. Whatever it's for, whether it's for a point or 2 points or 3 points. Okay, because if you don't know the identity, you couldn't possibly be working apply it. You'd be starting out with a bad premise. Everything's downhill from there. So it's super important that you have these memorized perfectly. Okay, now you could switch those two up, I guess, because that's the commutative property, right? Commutative property of multiplication. And you could switch those two up. But you can't go like take this here and this there around that negative. So those are the examples for sine. If you go to cosine, entirely different. The cosine of alpha plus beta, instead of doing like sine, cosine, cosine, sine, it goes cosine, cosine, sine, sine. So it's going to say cosine of the first and times cosine of the second. And then it's going to go sine of the first, sine of the second. And if that's a plus, this ends up being a minus. So it switches the SIGN, whether if it's positive, it goes to negative. But nicely, the cosine of the one that's alpha minus, it's positive there. And then the tangent, although the proof is kind of helpful on that one, it's not super ultra helpful. The tangent kind of starts out looking like a distributive property. The tangent is a fraction. The tangent of alpha plus beta, So you're going to start out, it looks like you're actually doing the distributive property. Tangent of the alpha plus tangent of the beta. And then you draw a line, and whatever you just wrote, those two terms, multiply them together on the bottom. Kind of leave a little space here on the left. So I'm going to multiply the tangent and the tangent on the bottom. And then you either go 1 plus or 1 minus, depending on what this sign is. If it's plus, you're going to go 1 minus. If it's minus, you're going to go 1 plus. So that would be the alpha plus beta for tangent. And then here would be the tangent of the alpha minus beta. Again, start like you're distributing it. Right? Tangent alpha minus tangent beta. Take those two, put them on the bottom, tangent alpha, and multiply them. And if that's a minus, change it to a plus and add it to the 1. And we don't learn alpha plus betas for any of the other 3 trig functions because, for instance, if I said, hey, what's the cosecant of alpha plus beta? Couldn't you say, well, cosecant's the same thing as 1 over sine, right? Right? We know that. So if cosecant of theta is 1 over sine of theta, then cosecant of alpha plus beta is 1 over sine of alpha plus beta. So if I ever did ask you something like that, I would just go and take that identity and find it and get my answer and just put a 1 on top. And I could do that with a formula too. I could just put that whole formula right there on the bottom of 1. Y'all with me? So I'm going to ask you, I'm probably going to pick one of these and one of these and one of these, and they're probably worth 3 points. And actually on this first test, what did I do? Yeah, on the alpha plus betas, I made those 3 points apiece, and I probably just picked one of each. And that's 9 points. And then the other 11 points are fundamentals that technically we've already been talking about. I don't think any of the fundamentals were completely new to you. We had gone over them in some form or fashion. Y'all with me? So you definitely don't want to miss these. So I'm pushing this quiz to Monday. So you got a weekend to make some flashcards or whatever. I would practice not just saying them, but writing them, because that's what you're actually doing on the quiz. Simulate it as best you can. And on this one, I'm pretty sure I'm going to give you like the left side. But what you have to be able to do eventually is like if I said something like this is an example what you might see. Sine of 10 cosine of 80 plus cosine of 10 sine of 80. What does that look like? That looks like this one, doesn't it? So what is this equal to then? The sine of 10 plus 80, which is the sine of 90. And you know at 90 degrees, what's the sine value? 1. So all of that simplified to 1. So that's the kind of thing you would do. Most of the time when you're applying these, you're either given a situation like this, which you're kind of going backwards, or I'm given an angle like, for instance, what if, this is a terrible example, but like, what if I said, this really is a terrible example. You don't use it this way, but you know what? I'm not even going to give it. It's terrible. Terrible. If you're Charles Barkley. You with me? Okay. All right. So, go to your book. Actually, I am going to show you this proof. And then you notice there was no homework last night. I was thinking there was too. I was just a day off in my head. But I gave you some practice problems on simplifying more complex identities using the trig identities that we have, right? It's kind of like, listen, in today's day and age, if you work, I'm not going to say manual labor, but if you're more of a blue collar industry, there's a tool for everything. There really is. I mean, it's amazing the tools that are out there. Now, they're not all cheap, but a lot of times you don't have the right tools and you make do with the tools you have. And that's kind of the idea of identities. There are an infinite number of trig identities, but we can't have them all. right? It's like you can't have every tool. Sometimes you just got to make do with what you have. And the ones I have you memorize are enough. It's like, I don't want to hammer a nail in with a shoe, but if I had to, if it was a strong enough shoe, maybe not like a tennis shoe, but if I had like a good, dress shoe with a heavy heel or whatever, I could probably get a nail in or a rock or whatever. I could do something. So it's kind of like that. The identities we have, they're not all of them. So a lot of times I'll give you identities and say, hey, take this identity and simplify it, or take this expression and simplify it using the tools you have, the limited ones I'm asking you to memorize, and usually those are enough to get you where you need to be. Not always, but usually enough. All right? So we are in somewhere around page 35-ish. I'm going to go and show you this proof. Now, a lot of you are going to look at this and your brain's going to freeze up a little bit, and you're not going to like this a bit, and that's okay. But I want to show you where the alpha plus beta's identities come from. And I'm going to start with, and again, in a million years, I would not have come up with this, I don't think. I mean, maybe if I was trained formally to do proof, but I don't think this is naturally something I would think of to find the cosine of alpha minus beta. But somebody out there, long time ago, came up with this proof to how to write that identity that we just learned. And this is what they did. They said, okay, they're going to call alpha the angle in standard position. Remember what standard position means? It means one side points at 0. So they're going to call alpha the angle that goes through in standard position through point P. So that means that this angle right here is alpha. That's what they're calling alpha. And I would have drawn better pictures, but I didn't know how to do this other than manually. So you might want to fill this in as you go. Okay? Now, they also said the angle that's going through point Q, so this other angle in standard position, so I'm still pointing here, but this one's going through point Q. They're saying this angle is beta. So if the brown one is alpha and the pink one is beta, somebody tell me what this is. What is that? If this is alpha and that's beta, that's alpha minus beta. Are y'all with me on that? Okay, so I'm going to say that is alpha minus beta. So far, so good? Okay. If this is alpha minus beta, and I'm going to get rid of all this other junk once I've done that. You don't have to, obviously, because you're writing on it, but I'm just trying to make it clear. Is it true that if I rotated this, basically this little section right here, if I rotated it around so that the alpha minus beta doesn't change signs, and I brought it all the way around until that ray basically landed back here, couldn't that angle and that angle be the same if I was just really careful and did that? And if I did keep them the same so that this had the same measure as that, then wouldn't this length right here have the same length as that? Would that still be true? Does that make sense? So whatever this is, say this is 50. If I bring that over and that's also 50, well, if that's 50 and that's 50, then these lengths would also have to be 50. And I'm hoping this is to scale. It might be a little off with it. Now, that's the whole basis of their argument. What they're going to do now is they're going to find the distance from Q to P and the distance from R to S. And they're going to say if those distances are equal, then I'm going to have an expression with a whole bunch of trig stuff in it. You'll see that in a second. And if I have a whole bunch of trig stuff in there, maybe I can find a way to get cosine of alpha minus beta out of it. Let's see, because there is an alpha minus beta in there. Okay, so here's what they did. If this is a 1 unit circle, say this is over 1, 0, what would this right here? So I'm gonna erase everything else so it's really clear what's going on here. Now remember, the angle, I'm gonna leave the angle. The angle is alpha minus beta. Okay, so what is this point? I'm gonna help you out. I'm gonna bring down a perpendicular. And I want you to think about this right triangle right here. Okay, now you know that's the length of 1. how do I find this height, this y, and that x, so that I can get this point? How would you do it? We've done this before. I've got a trig function. I know the angle is alpha minus beta, and I know that side is 1. What can I do to find y? Sine?
Y.
So sine of alpha minus beta.
Sine of alpha minus beta equals y over 1.
Equals y over 1. So basically, sine of alpha minus beta is y. Okay? And then how do I find this x?
Cosine of
Alpha minus beta. Ooh, I already got it in the problem. That's x. So that's that point. So if that's that point, and you already know this is 1, 0, can I use the distance formula to find that distance? I think I can. All right, let's go over here. How do I find Q? Now remember, if I brought down a perpendicular, right? Let's think the exact same way. If this is do that. Let me make sure of something. Okay, that's right. I want to get y'all out. I'm going to ignore this alpha minus beta right here. And I'm going to go back to the fact that this big one was alpha. Okay? So if that big one's alpha, using that same thing, that's alpha, but I'm thinking about it like it's right here. And remember, this is a unit circle, so it's 1. How would I find that y and that x if the angle now is alpha? Same way, right? The cosine of the alpha is always x over 1, and the sine of the alpha is y over 1. So you don't really need that 1 there. And guys, isn't this what the unit circle did anyway? When you think about the angle, isn't the cosine of the angle always the x value? Think about 30 degrees. Isn't the cosine of the 30 that, and the sine of the 30 that? So if I have an angle like alpha, then this point right here should be cosine alpha, sine alpha. Just like this one was cosine alpha minus beta, sine alpha minus beta. And if I have this angle is beta right here, what should I know about this point? What is it? If that was 120, how do I find the x?
Oh, no.
I'd go to the, if that was 150, how would I find the x and the y? I'd go to the unit circle. What's the x? The cosine of the 150. What's the y? It's the sine of the 150. So if that angle is beta, how do I find the x? Cosine of the beta and sine of the beta. That's how I always find it. Now, normally I would say the cosine of the angle is x over r. That's always true, right? That's your trig function. But what's the r?
1.
So guys, you know that, right? The cosine of any angle is always x over r. And if the r is 1, this is always going to be true. Doesn't matter what the angle is, where it's located. Always true. So if you know the angle, cosine angle, sine of angle. If you know the angle, cosine angle, sine of angle, cosine angle, sine of angle. Now I want you to think, if my goal now is to find this distance, and it's got to be equal to that distance, then I should be able to take these 2 points and these 2 points and do the distance formula. And that's what I'm doing. Check it out. If I have these points, I'm going to take here. Just keep in mind those 4 points right here. Starting right there. The 2 x's of P and Q are right here. So I'm going x minus x, x minus x squared, y minus y minus y squared. Over here, x minus x, it doesn't matter the order, x minus x squared, y minus y minus y squared. Are y'all seeing that? And I put them both under the square root. And then I square both sides, and when I square both sides, I lose the radical. Now that gets me to here. So let's look at the magic of algebra at this point. So how do I square something minus something. What's our rule for squaring an x and a y? Square the first, square the last, that times 2. Square that times 2 gives me negative 2 cosine alpha minus beta. Okay, so that's this first part right here. Then how do I square this? Oh wait, the zero's gone. So how do I square, actually it goes to there. How do I square that? Just square it. Right? How do I square this? Square the first, square the last, that times 2 gives you the middle. So there's that part. Square the first, square the last, that times 2 gives you that part. Now, do you see any trig identities in there? What's cosine squared blah plus sine squared blah? What's cosine squared alpha plus sine squared alpha? That's 1. So all of that becomes a 1, and I add the 1 to that, and I get 2. And then I just bring that part down. What about this? Cosine squared alpha plus sine squared alpha. Another 1. Cosine squared beta plus sine squared beta. Another 1. That gives me that 2. And then I bring the other stuff down. And at this point, the 2's cancel. And now I have this. And at this point, I look up here, and everything has a negative 2 in it. So what can I do? Divide out the negative 2, which makes that positive, and what do I have? I have an identity that relates alpha and beta when you're subtracting. So that's my first one. Now I'm going to make a little clever substitution and use my even and odd identities that you learned yesterday to come up with all the other ones. So check this out. What would happen if I said let beta, just another angle, equal a negative theta? So I'm going to plug negative theta there, negative theta there, negative theta there. So what does this simplify to? Cosine of alpha plus theta. So the sum of 2 angles. Doesn't matter what I use, whether it's alpha, beta, A, B, X, Y, happy face, banana. I mean, you could use any 2 symbols, right? What's cosine of negative theta based on your identities you learned and thought you were going to be quizzed on today?
Negative cosine?
Nope.
Or no,
regular
just
cosine, right?
Just cosine.
So I can just throw that negative away. What is sine of negative theta?
Just sine.
I would factor a negative out. Know those identities. I would factor it out.
Cosine and cosecant that are always positive.
Cosine and secant. So I would factor that negative out, and if I'm going to factor it out, I got to factor it out at the very beginning. And that's why cosine of alpha plus, and granted, again, I don't have to use betas, alphas, x, y's. If I have a cosine of a something plus a something, cosine first, cosine second, change the sign, sine first, sine second. So now I've proven the cosine identities of alpha plus beta. What about the sine identities? Well, to do a sine, didn't you learn yesterday on the cofunction identities that the sine of any angle is the cosine of its complement? So like the sine of theta is cosine of 90 minus theta? So isn't the cosine, the sine of blah is the cosine of 90 minus blah? Isn't that true? So I said, okay, if I want that, I just need to do this. But wait a minute. If I take this right here and distribute the negative in, I get to here. And then I group that together, I get to here. Okay? Now let me ask you a question. If I get to there, isn't this kind of like a cosine of angle minus angle? Right? And if this is a cosine of angle minus angle, isn't your rule to go cosine of the first, cosine of the second, change that, sine of the first, sine of the second? Isn't that your cosine of angle of something minus something? Yes? Got to get a little creative to do that. And then right here, what's cosine of 90 minus alpha? What is your cofunction identity tell you? Sine of alpha. So I can replace that with that. What's sine of 90 minus alpha? Cosine of alpha. And then I have my alpha plus beta sine. And then to find the one that's minus, I do it like I did before. I let b equal negative theta. I replace that with a negative theta, that with a negative theta, and that with a negative theta. What's your rule on cosine of negative thetas? What do you do with the negative? toss it. What do you do with the sine of negative theta? Bring it out. And now I have a sine of alpha minus theta, which is like angle minus angle. And what is the sine of angle minus angle? We already talked about that, right? Sine of the first, cosine of the second. Keep that cosine of the first, sine of the second. Those are your four identities. And the tangent one probably makes sense, but it's a little bit more weird. Well, it's not weirder algebra. It's probably a little more straightforward algebra. Isn't tangent defined as sine over cosine? Yeah? So if tangent sine over cosine, couldn't I rewrite tangent of alpha plus beta is sine alpha beta plus cosine alpha plus beta? And just plug those two identities in there? Now, you might look at that and go, why didn't they just use those? You could have. There's a zillion identities, right? We can't have every tool on the planet. Heck, you go into Home Depot, there's a wall of different kinds of hammers. And then there's a machine that just shoots nails. I mean, I've got 3 of those. One that shoots tiny little staples, one that shoots bigger staples, and one that shoots full-grade nails. So there's all kinds of tools, right? We got all kinds of identities, but we only need to memorize a certain number to be able to balance out. So how do I create this one? Well, you got to get kind of clever. So here's what they did. They went in there and said, what if they divide everything by that? Now, are you allowed to divide? Like if I have a fraction like 4/12, can't you divide the top and the bottom by 4 and get an equivalent fraction, right? That's a rule. So if I have a fraction, I can divide the top and the bottom by the same thing. It's like multiplying the top and the bottom by the same thing. So I'm going to divide the top 2 parts right here by cosine alpha, cosine beta. And I'm going to divide the bottom 2 parts by cosine alpha, cosine beta. And that's what I'm doing here. But look what magic happens. First, everything cancels here and leaves me 1. Here, sine over cosine, tangent alpha, sine over cosine, another tangent alpha. Here, those cancel. Sine over cosine, tangent alpha, sine over cosine, tangent alpha. And that's where that identity comes from. And then once again, you could do the whole beta equals negative theta deal, and you can plug that in there to try to get the alpha minus beta formula. So I did. I plugged beta, negative theta, negative theta, negative theta. And what's the rule on tangents? What do you do with the negative of a negative angle?
You bring it outside.
Bring it out. That's why that went to negative. And what do you do here? Bring it out. That's what I'm positive. So those are your identities. You don't have to know those. I'm not going to make you prove them. This is not a proof class in college, but that's where they come from. All you have to do is memorize them along with those other fundamentals. And if you do, you're going to have a good start to quiz week. But this will put a quiz on Monday, Tuesday, Thursday. Are you with me? And we only have a 4-day week, so that's almost a quiz every day. That's 60 points. I'm trying to hand them to you. If you make some flashcards, you can get those. If you don't, every year I have somebody makes a 4 out of 20. Man, all I forgot was the plus. It's right or wrong on these. So you got to be right, okay? All right. And this is an example. I don't know if you noticed this in your book. Here's some examples of problems. Let's see where you are. What is that?
Wait, what page is this?
This is page 41. That's what? Cosine on the right. Secant, because that's a co-function. So if it's cosecant, it's related to secant of what? Theta. What's this? Cosine theta over sine theta. What's that? 1 over tangent theta. You're getting all these right. You got a good start. 1 plus cosine squared. Sine squared. Be careful because sometimes I write cosine squared minus 1, and that would be negative sine squared. So be careful. Tangent squared plus blank equals secant squared. 1. Sine squared plus blank equals 1. Cosine squared. Cosine of negative u. Cosine of positive u. Cotangent of negative u. Negative cotangent u. Sine squared theta minus 1. Negative cosine squared. And if you need to write out the full identity and move stuff around to see that, that's what I do in my brain. If you need to write it out. Help yourself out. Cotangent of 20 equals tangent of 70, because the 90 minus 20. Sine cubed 13 plus cosine, sine squared 13 plus cosine squared 13. 1, because it doesn't matter as long as the angles match, right? Sine of alpha minus beta. Let's see. Sine of the first Cosine of the second.
Minus.
Keep that. Cosine of the first. Sine of the second. Great. That would have been a +3 if that happened. What is that? That's the tangent of what? Alpha plus or minus? Minus, because remember it's the top side. It's like the distributive property happened on the top. So that would have been the minus. All right, here's some trickier questions. When I say trickier, I don't mean like life-changing trickier, but some of them are a little trickier. What is that? Do you have an identity that has a 1 and a secant squared in it? Yeah, so what's the answer? You're right, tangent squared, you just missed it. Negative tangent squared, right? Because it's tangent squared plus 1 equals secant squared. So you would have subtracted the secant squared and you have to subtract the tangent squared. What's, oh, well, let's jump to 17. What's that? -1. And then the trickiest one on there, what's 16?
51.
Now, you're right, but I bet you're right for the wrong reason. Sine of 70 is cosine of 20, right? By your Pythagorean rule. Sine of 70 is cosine of 90 minus 70, so 20. And then if there's two of them, you just bring down the squared, and then now you have a what? Pythagorean must be equal to 1. But if you did this, sine squared of 90, sine of 90 is 1, 1 squared is 1, you got lucky. And that, I can rewrite this question so you won't get lucky. It's like if I made it with that same thinking, you would do this on cosine. If I made that the question, you're going to go cosine squared of 90. And what's cosine squared of 90? Well, cosine of 90 is 0. And you would have gone 0 squared is 0. But that's not true. Because what is this? Well, what's cosine of 20? Sine of 90 minus 20. So sine of 70. Well, if it's squared, you just got two of them. And what does that mean? 1. So you can't just add those. If you're like, why not? Well, guys, look. If you could add sine of an angle plus sine of another angle and get sine of 90, then aren't you saying this? But we just learned that's not the formula for this. What's the formula for this? Sine of 20 times cosine of 70, and then cosine of 20 times sine of 70. So clearly, if this isn't equal to that, then there's no way that's equal to that. This is not true. You cannot do this thinking here. So that's a trickier one, but I've shown it to you. You're just forced to get creative on a situation like that. And if you're like, well, couldn't I take my calculator out? Well, that'd be great if it was a calculator question, but that'd be awesome. But it's not going to be a calculator question.
Wait, so you just, did you do 1 over cosine squared?
Again, I just said, I noticed that these two are complements. And I've got an identity that relates complements. So I could change either one of these, it doesn't matter. I can change sine of 20 to cosine of 90 minus 20.
My bad.
And then now I have a Pythagorean identity. Or I could change that to cosine of 90 minus 70, which is cosine of 20. Either way, they start matching, and I get 1 in this case. I've asked that question probably on every test I've ever given in Algebra 2, maybe even in pre-cal, just to throw it out there, because occasionally it's like a ciphering question. And it's like the easiest ciphering question probably ever, because you don't even have to do work. You just have to see that pattern. Well, if you don't see the pattern, it's not easy, though. Okay, let me just do a few more of these. I've gone through all that. We really did a lot of the work we were supposed to do yesterday. Yesterday. So let me just throw a few more identities and see how you're doing with all this stuff. And we have, what? 15 minutes. Should be plenty. All right, so what? something. I forgot to do scantrons. We got to do scantrons in a second. Because that's, I had to do 6 peoples. My hand was cramping up.
Oh, yeah.
But it's awful. Simplify means PEMDAS, but on Trig, it means your Kevin Hart list, wherever that is, right? When you see simplify here, am I going up or down, or I'm totally in the wrong spot? Yep. That means, that's something else here. That means you're going to go in here and you're going to try to clean it up as best you can. And if you get stuck and you're like, I think I could do more, go and use these suggestions right here, but never just stare at it, okay? We try to do something to get there. And then you can ignore that one for now. We'll get to that later. So here we go on some of these random examples. So first one, what would you do if I gave you this? Does this look simplified to you? Looks factored to me, which is opposite of simplified. No F in PEMDAS either, right? How do I simplify that thing, do you think? Maybe multiply together. So 1 times 1, outer, inner cancel. That times that's negative sine squared theta. Oh, wait, that looks familiar. What's 1 minus the sine squared? Cosine squared. Once you get it down to a single term, unless it's on the denominator where you could bring it up, I feel pretty good about being finished. All right, what about this? Sine of x over cosecant x plus cosine x over secant x. Anybody got any ideas? Change it all sines and cosines. How would I do that? So really changing it to sines and cosines and putting everything in the numerator is kind of the same thing, right? Or using a fundamental identity. So a cosecant in the denominator of a single fraction would be the same thing as a sine of x in the numerator, right? Which would give you what here? Sine squared. And then over here, a secant in the denominator is the same thing as 1 over cosine, but we give you a extra cosine in the numerator, which gives you cosine squared, and all of a sudden, for 1. What about, let's give you something a little more challenging. What about this? Actually, I don't know how challenging this is. A lot of ways you can do this. What about this? Anybody? Okay, that's one way. I'm bringing this up. I can't bring it up with just one term. This is one single binomial. So if I brought it up, I would have to group the top part, right? And I could make it a cotangent. We'll do that next. So if we're doing it this way, I've done this. What are you going to do? I mean, if you've already done this, I could change the sines and cosines. Don't bail so quickly. What if I distributed it? What's cotangent squared times 1? What's cotangent squared times tangent squared? Aren't they reciprocals? If they're reciprocals, what should you get?
1.
What's cotangent squared plus 1? Done. Now, another way, you said, what was the, you said change that to what? So I could also change the top to secant squared because that's what that is. And that would give me this. And then what could you do? And try something. All y'all are doing number 8. You're sitting and staring at it. Shame, shame. Do what? Change it to sines and cosines. What's secant then? 1 over a cosine squared. What's tangent squared? Sine squared over a cosine squared. How do I take one fraction and divide by another fraction? Multiply by the reciprocal. Wouldn't that give me that? Which then that cancels. And what's 1 over sine squared? So there's always a way to get there. It might be, your journey might be different than his or hers or mine or whatever, but we can still get there. What about, I'll do one more and then we got to do skin tones. What about this? You know what? I'm doing these skin tones. I am not bubbling these things in. We'll come back if we have a second. Are you going to be early or on time? Okay. Yeah, I filled yours out, gave it homework already, but he said he'll bring it.
Okay.
Over at 8:30. What time y'all gonna be there? 8:45. If you're sitting at 8:45, that's totally fine with me. That'll give a moment or two for stragglers, or people whose parents are late, or in case your mom hadn't had enough coffee and she starts yelling at you. Okay, so guys, I'm about to give you your student number. Your student number goes in that box that says, everybody have a pencil? Everybody got a pencil? Okay, here's your number. Everybody starts with, 104. This is in student number. Right there, it says space for student ID or student number, whatever. Okay, everybody starts with 104257. So those first 6 digits, everybody's the same, 104257. And then here are your last 3 digits. Isaac, you are 100. JW, you are 110. Ryan, you are 120. Russell, you are 130. Holden, you are 140. Abdul, you are 150. Camille, you are 160. Sonny, 170. Lily, 180. Sam, 190. Sam Gray. Sophie, 200. Kate, 210. James, 230. Thomas, 240. Susanna, 250. Sam Sutton, 260. And Kaylin, 270. Now, you're going to bubble that number, and you're going to go last name, first initial. And I don't think, except for Millie Kate, you need to go both initials, first and middle. But other than that, I think everybody, I don't think anybody else has a matching name. Yeah. Okay, now, so last name, first initial. Now, also, let me show you this. You have to do this in all caps, they have said. So check this out. In all caps. Okay, everybody look up here. Okay, so if you turn your answer sheet so that, like you're going to be filling it out, there's no box for this, but above school or organization, above that, print in all caps. So there's a box here for organization and for name of test. Above that, in between answer sheet and that line, there's no box, but just print your first and last complete name in all caps. And then, once you do that, below that where it says school or organization, don't put HHS because there's Hansville High School, Homewood High School, Hendersonville High School. Right, Homewood High School or Homewood HS, and then Algebra 2. Everything in all caps. And I think that's because they might have old eyes and because some people's handwriting is atrocious and they figure all caps is a little easier to recognize stuff. So don't worry about anything else, but you got to have your student number, your name bubbled, and then those 3 things right here. And then Algebra 2. And when you are finished, it should be shortly, I want you to trade with someone. and you can do multiple trades. And you are going to look at their paper. And if they have a mistake, you're going to verbally accost them. I'm just kidding. No, you're going to look at that and you're going to point out their mistake. Make sure you look at, hey, check the number. Make sure they bubbled the correct number that I gave them. And make sure they have those 3 pieces of information. And if their bubbling is atrocious, maybe point that out to me so I can maybe clean it up for you.
Are we supposed to put the second initial?
You don't have to have that middle initial.
Oh, okay.
Unless you're MK and MS. Right. All right, now once you have that done, let me get this from you.
I am smart. Yeah, I should be verbally abused right now.
Accosted. He is a little too aggressive. Accosted. I don't know if you all even read my syllabus. I know back in the red and blue days, those were dark days. But I used to say, I think I still have it in there where if you sharpen your pencil
Oh, yeah.
to verbally accost your classmate or whatever. I used to have people do, nobody really sharpens it anymore.
Oh, dude.
Hey, do I have everybody's? Have everybody's? Everybody. Y'all smell like somebody's smoking?
No, it smells like.
Who is it?
No, it's been all day long. It's, when I walk back through there, at first I thought, oh, somebody's a smoker in here. But every period I've done this, right in there, like, is there something? No, like in first period and third period, like, I don't know if there's a vent and it's like piping in air from a intake where maybe like some teacher's outside taking a toke or something. I don't know. But and maybe it's this stupid thing I'm wearing. I don't know. But I've been like, do I smell a cigarette?
Mysterious secret someone has.
All right. Yeah, we don't have time. I'm glad I started. All right, guys. Well, I will see you at 8:45. Set a couple alarms. If you sleep through alarms, have a backup. I really need you there on time because we got to start at 9 sharp. We can't wait.
Oh, yes. We got third place.
Oh, and I heard, not that I'm afraid of a challenge, but I heard Mountain Brook's not bringing an algebra 2 team, just a comprehensive team. So we won't even get a challenge from them.
So bad.
So I have a good feeling we'll get people to beat down. Although they are bringing 5 people to comprehensive.
It doesn't matter.
If I know
It
this
doesn't
guy,
matter.
Hey, you don't know this dude, man.
They're gonna get tough.
Mr. Hurry,
Genius wears off, man.
we'll handle him. Don't worry. We'll handle him.
I'm a little concerned about
We'll shut
comprehensive.
down. We'll lock them up.
We'll see.
Right.
Look, I always do that with
How
my.
can you lose this big prize?
I always do that with my hands when I'm running. I can stop it. Isn't that weird?
My goal is just sweep, man. Top 10.
Yeah,
What am I
maybe,
doing?
weird.
Now, my goal is that last year was the first year where we not only won all 3 divisions, but we had first place in all 3 divisions. We haven't ever done that. So it's tough to repeat that, but
It's okay. We have JW still.
This is not Brooke, first name. Wait, is it finger?
sorry?
Last minute.
Yeah.
He just loses his eyes.
He's
He's gonna be back in the.
He was prepared. It'll be a pretty tough match. But I doubt he will teach you. He's just showing up. And I doubt, knowing Hugh, that he did a lot of preparation. I know Michael Mormon did,
Look around at all these.
because I think Michael wants to beat you because he lost you by like a point last year. But Michael will be there. Brandon's just pretty good. And he cares. And sometimes he knows more than me. He's got little secrets that he learned this stuff in Florida when he was down there, doing this map count stuff. He goes, you know, there's a little trick for that. I'm like, so,
I sit next to him in chemistry. All the
I know.
Turing, we're gonna game tonight if you'd like to come. It's
I got fun.
here.
Here, so out there, it's so fun.
At 5. At 5.
At 5? Okay, my wife is maybe coming home tonight. It's her birthday weekend, but she's in South Florida with her mom because she's getting this transfusion thing. If she doesn't, maybe I'll be able to get there.
Okay.
So is that a big game?
Yeah, they're number 1. They're so good.
Have they lost yet?
They lost to the same person we lost to. Like, we beat Oak Mountain 1-0, they beat Oak Mountain 1-0. They lost Huntsville 2-1, we lost Huntsville, or 2-0, we lost Huntsville 2-1. So, like, it's gonna be like,
Really? And Huntsville's large school?
yeah, we both should have won now against them.
Ah, there is a close one. Now, y'all have friends over there?
In Huntsville?
No, in West Davis team.
Yeah, I do. One of them's like plays like opposite positioning, so she'll be like I'll be on her.
Ah, nice.
Yeah.
All right, I'll try. 5 o'clock.
Okay.